KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
Work done by a variable force, right? So in our last class, we focused to discuss what is the work done due to variable force. In our previous classes, we discussed work done due to the constant force. So in case of constant force, work done is the product of force and displacement, right? So force is a vector quantity and displacement is also a vector quantity. When you are multiplying two vectors, that is scalar product. So the scalar product of two vectors will give us the scalar product of two vectors, force and displacement, will give us work. But this is in case of constant force. But whereas if you go for variable force, right? So variable force means either the magnitude or direction or both continuously changing with time. Continuously changing with time. Okay. So when the force, the magnitude or direction continuously changing with time, it is said to be variable force. When we are going to calculate the amount of work done due to variable force, we have to concern the integration. So the summation symbol and then integration that we discussed in our last class, right? So the formula for work done regarding the variable force is integration xi to xf f of x dx, right? So xi is the initial position, xf is the final position, right? That is. So now based on that work done due to the force that we are going to calculate with the help of one example problem. Afterwards we are going to discuss work energy theorem for a variable force and then we are going to discuss some other example problem, right? Okay. So first I will explain you first example problem 6.5. See here, a woman pushes a trunk on a railway platform which has a rough surface. She applies a force of 100 newtons over a distance of 10 meters. Thereafter, she gets progressively tired and applied force, whatever the force she applied, reduces linearly with a distance to 50 newtons. Full stop. The total distance through which the trunk has been moved, the total distance through which the trunk has been moved is 20 meters. Full stop. Plot the force applied by the women and the frictional force. Plot the force applied by the women and the frictional force which is 50 newtons versus displacement, right? So calculate the work done by the two forces over 20 meters. So my sincere request is please try to understand the problem. So in our physics, understanding problem is very important to get the correct answer and to get the solution as much as short time, right? So it is the situation. This problem example 6.5 is the situation. So what's happening that he is giving. Based on that he will ask some quantities to calculate that we can, right? So you just every line you have to imagine. See here, a woman pushes a trunk on a railway platform which has a rough surface. A woman pushes a trunk on a railway platform which has a rough surface, right? Next, she applies a force of 100 newtons. She applies a force of 100 newtons over a distance of 100 meters. She applies a force of 100 newtons over a distance of 10 meters, right? Next, so when it is going to travel the distance of 10 meters, she applied 100 newtons. So whatever the force she applied, that is with respect to distance he is giving, that we have to keep in mind. That is what 100 newtons over a distance of 10 meters, right? Next, thereafter, after completion of that, aprama, okay, adikapram, she gets progressively tired. Generally, you know very well, one fact is, if you are applying the force continuously, we will tired now. That is the situation here. She gets progressively tired, and her applied force reduces linearly with a distance to 50 newtons. Reduces linearly with the distance to 50 newtons. So again here he is talking about that force with respect to the distance. Full stop. The total distance through which the trunk has been moved. The total distance through which the trunk has been moved is 20 meters. Okay, full stop. Plot the force applied by the women and the frictional force. Plot the force applied by the women and the frictional force, which is 50 newtons. So he is asking to draw a graph. Between what and what? Force and distance. Right? Next, calculate the work done by the two forces over 20 meters. Calculate the work done by the two forces over 20 meters. Right? Okay. And one more important point I want to say regarding this problem. He used distance. Distance means distance is actually scalar quantity. But you have to keep in mind what is the difference between distance and displacement. Right? Displacement is the shortest distance from initial position to final position covered by a body. Right? Before that, distance is the actual length of the path travelled by a body. Distance is the actual length of the path travelled by a body. So this difference, distance between displacement, we have to keep in mind. That is very important, because I am talking about sometimes distance. Distance means you don't think that where is the distance, right? Because in case of definition of work is the product of force and displacement, not the distance, right? But here I am talking about distance, means you understand what is the difference between distance and displacement, right? So distance is the actual length of the path travelled by a body, whereas displacement is the shortest distance from initial position to final position covered by a body, right? Now we are going for solution, ma. So this is the solution, right? See here. It is the solution. See this. It is what force, okay, and it is what distance or displacement here, right? It is the displacement. It is the positive y-axis. It is the negative y-axis. It is the positive x-axis. Right? So in this graph, right? In this graph, which is force versus distance or displacement, right? So I already told you why I am writing sometimes distance, right? See this. So it is the positive y-axis, negative y-axis, right? So you know that it is the positive x-axis. On x-axis we took the displacement, that is what 10 meters and 20 meters, like that. Here it is 0, 50, 100, right? I think you know how to take the scale on x-axis and scale on y-axis. It is our wish, but here you are taking 10 meters means the next also we have to take 10 meters, like that. Here we are taking 50 newtons means here also you have to take as 50 newtons, right? So it is again 50 newtons, but it is minus 50. It is plus 50. It is again 50. It is 100. It is minus 50. It is the 0, right? So it is the graph. It is the x-axis. Okay, right? So if these are the points, A, B, C, D, E, F, G, H, I. These are the points to represent different points on the graph. So you just see the situation. First 50 meters, right? From here onwards. See, she applies a force of 100 newtons over a distance of 10 meters. See this. 10 meters over a distance of 10 meters over a 100 newtons over a distance of 10 meters. See this. Afterwards, what is happening? See here. She gets progressively tired and her applied force reduces linearly with a distance to 50 newtons. See here. Reduces linearly with a distance to 50 newtons. Okay. Right. Afterwards, observe carefully. The total distance through which the trunk has been moved is 20 meters. Here, he didn't say anything. What is that? What about the distance? He didn't say. But afterwards, see, based on this, we have to get here the distance is 10 meters. So, from 10 to 20 is 10. Gap is 10, right? Okay. Now, after this, what he is saying? Okay, it's a question like Platt asking to draw the graph. Platt the force applied by the women and the frictional force. Okay, right. So, this is the graph, right, ma? Clear. Now, based on this, he is asking to find again, calculate the work done by the two forces over 20 meters. See this. At x is equal to 20 meters, what about F 50 newtons? See this. 50 newtons, right? Is not equal to 0. Is not equal to 0. At the same time, they have given that frictional force F is 50 newtons. Frictional force F is 50 newtons. And you know very well, what is the role of frictional force? Frictional force opposes motion and acts in a direction opposite to the applied force. Frictional force opposes motion and acts in a direction opposite to capital F. Okay, right, full stop. It is therefore, as shown in the figure, the negative side force axis. See this. This is the negative side force axis now, right? So, it is therefore shown on the negative side of the force axis. Right. Next, the work done by the women. The work done by the women. So, what is the work done by the women? We have to find. He is asking to calculate here. So, the work done by the women is. So, you know very well, if you find area under the force displacement graph, you will get as a work, because work is equal to force into displacement, no. So, it is like y into x. So, here if you want to find the work done due to the applied force is equal is area of rectangle ABCD, plus area of the trapezium CEID, right? So, here if you will find the area under this rectangle ABCD and area of this trapezium CEID, then automatically it will be the work done. That is what? 1750 joules, right? So, what is the formula for rectangle? We know. And what is the area of trapezium also? We know. It is 1750 joules. Similarly, next it is the work done due to the frictional force. It is the work done due to the applied force. It is the work done due to the frictional force. Here, it will be area of the rectangle. AGHI. Right. So, here WF is equal to, formula is same now for rectangle, length into breadth, but here it will be like this, minus 50 into 20, that is minus 1000 joules. You know very well, work is of different types, positive work, negative work and zero work also, right. So, what is the positive work, what is the negative work, what is the zero work, we came to know, we already discussed. Next, see here, the work energy theorem for a variable force. Already in our previous classes we discussed work energy theorem for a constant force, right. Now, discussion is work energy theorem for a variable force. See here, observe carefully. See, to prove the work energy theorem for a variable force, right, first we are going to confine ourselves to one dimension. The time rate change of kinetic energy is. So, generally mathematically time rate of change of kinetic energy means what dk by dt, that is equal to d by dt of 1 by 2 mv square, that is equal to m into dv by dt into v. See here, v square means v into v now. So, one v can write dv by dt, another one is v as usual. So, dv by dt means a into m, ma means it is f. So, f into v, that is equal to f into dx by dt, right. So, dk by dt is equal to f into dx by dt, dt will get cancelled, dk is equal to f into dx. So, this we are going to integrate, right? This we are going to integrate from xi to xf. Then what will happen? This is the next step. So now here we are going to apply these limits, that is what, kf minus ki, this side as it is. But what is this xi to xf integration f dx? From the work done due to the variable force concept, it is a work. It is a work. So finally what can we say? This is the work energy theorem, because work done is equal to change in kinetic energy. In case of one object, in case of one body, the change in kinetic energy is equal to the amount of work done. That is only work energy theorem, right? But this is the work energy theorem for variable force. See this, for variable force, right? For variable force. See here, ma. Okay? It is a variable force. So here it is f into v into f into dx by dt. Thus dk is equal to f into dx, f into dx, integrating from xi to xf. We have integration ki to kf dk is equal to integration xi to xf f into dx. Kf minus k, applying the limits, is equal to integration xi to xf f into dx. So kf minus ki is equal to w. So work energy theorem is proved for a variable force. Work energy theorem is proved for a variable force, right? So this is the work energy theorem for a variable force. Because of this, so this is the work according to the concept work done due to variable force, right? So we proved work energy theorem, but there is some information, you just focus on that. So in this information we will get the consequences. See here, when the work energy theorem is useful in variety of problems. Work energy theorem is useful in a variety of problems. Already I told you, work is a form of energy. The units of work and energy are same. The dimensional formula of work and energy is also same. So there is the difference between work and energy. The difference between work and energy as much as simple that we have to keep always in our mind, which helps us while solving the problems. At the same time, along with that, the work energy theorem also useful in solving a variety of problems, right? So here what I am saying is, it gives the complete dynamical information of Newton's second law. It gives the complete dynamical information of Newton's second law. It is an integral form of Newton's second law. It is an integral form of Newton's second law, right? Newton's second law is a relation between acceleration and force. Newton's second law is a relation between acceleration and force at any instant of time. That's already you know. Next, work energy theorem involves an integral over an interval of time. An integral over an interval of time. So here the temporal information means almost like time contained in the statement of Newton's second law is integrated over and is not available explicitly, right? So here what he is saying is, what is the relation between work energy theorem and Newton's second law of motion? Newton's second law of motion, right? And one more observation is, Newton's second law for 2 or 3 dimensions is in vector form, whereas work energy theorem is in scalar form. But you please understand, in Newton's second law we have totally 3 things: force, mass and acceleration. Their mass is a scalar quantity, force and acceleration are vector quantities. But here in case of work energy theorem, work is a scalar quantity and energy is also scalar quantity. Energy is also scalar quantity. Okay, right, that is. Next, example 6.6. Example 6.6, right? See here, now we are going to discuss another example. See this. Based on this, a block of mass, right? A block of mass small m is equal to 1 kg moving on a horizontal surface with a speed vi is equal to 2 meter per second enters a rough patch ranging from x is equal to 0.1 meters, x is equal to 0.1 meter to x is equal to 0.1 meter to x is equal to 2.01 meter, full stop. the retarding force Fr on the block, the retarding force Fr on the block in this range is inversely proportional to x, inversely proportional to x. Over this range, Fr is equal to minus k by x, minus k by x for 0.1 is less than x is less than 2.01 meter, is less than 2.01 meter. Fr is equal to minus k by x. It is a part of question and is 0. That is what? Retarding force is 0 for x is less than 0.1 meter and x is greater than 2.01 meter. So, when the x is in between 0.1 meter and 2.01 meter, Fr is equal to minus k by x. The same Fr is 0 for x is less than 0.1 meter and x is greater than 2.01 meter, where k value also given 0.5 joules. Next, what is the Kf and Vf? So, Kf means what ma? Final kinetic energy. What is the Vf? Final speed. Final speed of the block as it crosses this patch. As it crosses this patch. Okay. Right, see here. So, in this problem, he is asking to find. First, they have given mass value and initial speed also given, and they have given two values of displacement or position, right. So, based on that, they have given the value of retarding force also between that range based on that situation and equation. Then they have given k value also, right, asking to find what is the final kinetic energy and what is the final speed of the block as it crosses this patch. See here, we are going for solution. This we know very well. It is what? Work energy theorem. Kf minus Ki is equal to W, know. So, Kf is equal to Ki plus W. So, it is the W. It is the W, right. So, it is what? Integration xi to xf f dx. We substituted and we are going as usual. That is what? It is the formula is of mvi square minus k into ln x. It is what? 0.1, 2.01, right. It is of mvi square minus k into ln into 0.1, 2.01, right. So, here see this 2 minus, so this value we can calculate that it is what? 2 square ma, it is 4 will come and mass is 1, it is 2. So, 2 4 means finally it will be 2. 2 minus k value given 0.5 and it is log, right. So, 20.1, 2.01 divided by 0.1 means it is 20.1. Then finally, if you complete this mathematical process, 2 minus 1.5, that is 0.5 joules. Okay. It is what? Final kinetic energy, right. So, then you can find final speed, no, because k is equal to half mv square. So, here Vf is equal to square root of 2 kf by m. So, if you substitute this value and mass value also, right. So, you will get it as, right, you will get it as, because based on these values you will get it as Vf is equal to 1 meter per second, because it is 2 ma, it is 0.5, it will be 1 and mass is already given as 1. So, the final answer will be 1. So, it is 1 meter per second, 1 meter per second. Okay. So, this is about the solution what they are asking. Solution means the things what they are asking. One is final kinetic energy, another one is final speed, okay, right. So, what I am saying here is, in this class we focus to discuss one example problem, that is example 6.5. There we calculated, there we drew a graph, right. We drew a graph that is what? Between force and displacement, right. Afterwards, we calculated the amount of work done. Then we discussed work energy theorem for a variable force. It is important for board point of view, right, for 3 marks or 5 marks by giving some other example problem link to this concept. For NEET point of view, mains point of view, these formulas are important. Nowadays, we are getting problem on calculation of work generally based on the variable force only the problems are coming, right. So, that is you have to keep in mind. Afterwards, after completion of this discussion, that is work energy theorem for a variable force, we went to discuss some other example problem based on work energy theorem, right? So there they have given some values, So finally, based on values, we went to calculate the final kinetic energy and final speed according to the given question. Okay, right. Thank you. We will continue in the next class.